Hi, so today we're going to be talking about two different non-parametric testing is what we're going to talk about today. So the first one we're going to talk about is the Wilcox ranked sum test, and this is comparable to a independent samples t-test as far as parametric testing is concerned. So as far as what it can do, is compare between two different independent conditions, very similar to what a t-test can do. But in this case, we're going to want to use it when assumptions for the typical t-test aren't met. For example, normality and homogeneity of variance, things of that nature. So how does it work? Well, it works just like the name says. Ranks of our data are produced, and those ranks are then summed, and from there, basically, we have a W stat that's calculated, and that's calculated by subtracting the mean ranks from the sum ranks. And then from there, we have a p-value of that W-stat that we have obtained. And that is obtained either using a Monte Carlo or I guess you can call it a repeated samples method of your sample, or a normal approximation method. So in terms of assumptions, we don't need the typical ones, but we do want to deal with a continuous outcome variable and discrete predictor variable. So moving on, let's move on to my experiment. So I had previously brought my data in, but we will use code to bring it in a couple seconds here. But basically we have approximately 300 different participants, and half of those participants participated in a timed training module, and the other half participated in an untimed one. And then from there, we had two different administrations of the same test, and we have scores produced as our outcome variable. And we're kind of assuming that hypothetically we did control for retest things, for example, learning and maturation and things of that nature. So moving on, let's open some packages here, ClinFun and on, all the way until readxl. And then we're going to specify what we want to call this variable and use the readxl function here and contained in that package, and specify where our data is located. Then we're going to view the data using view non-parametric, which is the name of our data. Moving on, we're going to specify the data set as well as our variable that we would like to factor called condition here. Use the factor function, name our data set, and we're going to specify the factor as well, and our labels are going to be timed and untimed. We're going to factor that variable here. Now we're going to produce some summary stats. We have the traditional summary stats setup by function, I believe in the stats package. And we're going to specify our data set here, as well as the variable we're interested in, again, and we're basically dealing with the outcome and predictor variables in those spots there. We're going to use statDesc function, and that creates a very detailed output for us. And a little different here, we're going to use norm equals true, which is going to tell us about the Shapiro test, which is measuring the assumption of normality. And same thing here, the only difference is we're replacing score with score2 because that is our variable. Rather our outcome variable of interest in this case. Now we're going to move on and look at a different assumption here, Levine's test, and that's assessing the homogeneity of variance. We have our outcome variable as well as our predictor variable, and here we're specifying our data set. I'm going to run that. The only difference here is we're adding a different outcome variable, which is score2 or test administration 2. Now we're going to produce our our model rather here, produced by the Wilcox test function here. We're going to call it new model score condition. We're kind of creating a regression model type thing here, and this is our outcome predictor variable specifying the data. Very simple. We're going to produce that as well. This time, once again, we're substituting score2, and we're going to view our model just by specifying the model name within our code. And here we're just going to do a little bit different here. Basically the main difference in our code here is exact and correct, and basically what we're doing is, as you can see here, this produced a rank sum test with a continuity correction. We're going to take that away here, and we're going to view that as well, again by specifying the model name. And now if we're interested in the effect size between the groups, in case we did accrue significance, we're going to specify that using the function Wilcox model, n, That's the number of observations. Call it R from Wilcox. And basically what we were doing before, we did not have a z-value, which is needed for our case here. So basically what this lump of data is it's going to create a z-value using the q-norm function. And then we're going to plug into our function that we did create, R from Wilcox. We're going to specify the model name that we're interested in, as well as the number of observations, and we're going to do that twice. And that's going to produce effect sizes there. So I'm gonna move through my data here and talk about some interpretations. So first we're going to look at the Shapiro-Wilks test, which is contained in our summary stat summary stat function rather, that we did produce. And what we're interested in is our W values and the significance of those W values. As you can see, as we move down the line as far as conditions and outcome variables are concerned, it looks like in all cases we have violated the assumption of normality, which is a good thing in our case because we did use a non-parametric test. I always do randomize my data, so it is a coincidence that we did violate the assumption in our case, but typically you would probably do this, see that you violated the assumption, and then you would run the non-parametric test. So in all cases we did violate that. So now moving on to the Levine's test, it looks like we have not violated the assumption of homogeneity of variance because both tests in these cases are not significant, which is what we are searching for. So now moving on to the Wilcox-on rank sum test with our continuity correction in both cases as far as score 2 and score are concerned. According to condition, we do not have significance in either case. And when we do take away that continuity of correction, we're expecting to have a small change in our p-values, which we do have, but still we do not have significance in either case as far as new model or model 2 are concerned. So moving on, as far as our effect size is concerned, as expected, we do have a very small effect size, negative 0.05 and negative 0.09. Okie dokie. Sorry, I spoke pretty fast, and we're dealing with two different tests today, so I wanted to compress them into one video. So now moving on, we're going to deal with the Kruskal-Wallis test, which is basically comparable to a one-way ANOVA, one-way analysis of variance. We're dealing with multiple conditions and multiple independent means. So first, before we do everything, I'm going to clear my workspace just so I have a better view of what's going on. So what can this test do? Well, very similar to ANOVA, it can compare means across different conditions. And we're dealing with a little bit more complex of a setup now. So when should it be used? Well, when you're trying to run an ANOVA and the assumptions are not met, a non-parametric test just like this would want to be used. And how it works, similar to last time, the data is ranked, the ranks are summed, and then the H statistic is calculated, and that involves a chi-square distribution, a little different from last time. So as far as what it needs, the main assumption is just the setup of your experiment that's conducive to a one-way ANOVA. So we're dealing with possibly multiple predictor variables as well as a continuous outcome variable. So now we're going to move on to my experiment. So if we pull up the data here, which I did previously bring in, we're dealing with condition and score as far as predictor and outcome are concerned. And with condition, we're dealing with different levels of our variable. And as far as our factor is concerned, we're going to have high, medium, low, and none as far as our levels are. And that corresponds to what I'm looking at is job autonomy and job satisfaction level. So job autonomy we classified as none, low, medium, and high. And we're looking at job satisfaction, which could be an index score of, for example, the JSS. So we're going to want to see if there's differences between those, and this has been a previously researched subject, which it's been heavily looked at. So we're going to use library to open the various packages needed: carstats, PeerGMS, ggplot, and readxl. And now we're going to create a variable using readxl called Kruskal-Wallis, and we're going to specify where our data is located, and then we're going to view that, which we already did. Okay, so now we're going to create a factor. We're going to do that by specifying the data name and condition, the name of our factor, using the factor function, again, name and condition. And we're going to use some labels, high, medium, and low. And that's going to create a factor there. Sorry, that's a repeat of code. So now moving on, now we're going to want to create levels of the factor, and basically what we're doing is using the levels function to order our factor here. We're specifying 1, 3, 2, 4, which is how our data was imported. This would correspond to none, this would correspond to high. It's imported alphabetically, so we want to reorder that so it goes from none to low to medium to high. So that's what we're doing in this line. Okay, so moving on, now we're going to create some summary stats here by Kruskal Wallis, which is the name of the data, score, which is our outcome variable, and as far as our predictor variable here, stat desc, that's going to create a very detailed output for us, and norm equals true. That's once again similar to last test. That's going to allow us to look at the Shapiro-Wilks, so that produces our output there. Moving on, we're going to want to do the Levine's test to look at the assumption of homogeneity. So here we're using the Levine's test function, and we're doing our predictor variable as well as our outcome variable and specifying the data name. Okay, moving on. Now we're going to create our model here using the Kruskal test function. We're going to actually create our model. So we're going to call a new model, Kruskal test, which is the function here. Score, which is our outcome, predictor, and data. Pretty simple. Now we're going to want to view our model by specifying the data name in our code, and that allows us to look at it. And we'll go back in a second. Now we're going to want to rank the data using the rank function. So we're going to call it, it's our variable name there, Kruskal Wallis ranks. And we're going to rank it in the condition. So now we're going to look at a little bit different picture of our summary stats according to rank. And just to visualize what's going on, we're going to produce a box plot here using the box plot function score condition as before, and specify the data name, and now it's broken down into our different groups. So moving on, now we're going to want to get a little more specific here. We're going to use the Kruskal MC function. And what that does is it's going to allow us to do a post-hoc or post-hoc test, depending on how you say it. But on this one's a little more like a shotgun shell, and with that we can inflate our type 1 error rate. So we're going to use a little bit different of a function here. We're going to call it a two-tailed test. And what that's going to do is kind of control our error rate a little bit. And finally, we're going to do the junk here test. I'm not sure exactly how to pronounce this, but what it is a trend analysis. So we're going to use that function, Kruskal Wallis, that's our data, and that is our predictor. And we're going to specify as numeric to make it numeric, and once again our predictor in that. And we're going to run it, and that is our test. And while we're at it, we're probably going to want to analyze the trend of our second one as well. Sorry, that was a mistake. I should not have ran that. That score 2 was actually from the previous data set, so I thought I originally missed that, but I did not. So going backwards a little bit, now we're going to do some interpretation. So as far as the last one is concerned, similar to this one rather, we are looking at the p-values of our Shapiro-Wilks test contained within our summary stat output, and it looks like in all cases, as far as our w values, we do not have any significant w values, so we can assume that that assumption has been met, and the assumption of homogeneity of variance has also been met. So you may be wondering why you did a non-parametric test, but in my case I am always randomizing my data, and I wanted to do one of these, so it goes. So moving on, we're going to want to look at the rank sum test output, and as you can see in the one that we ran, our chi-squared value is not significant, so we can assume there's no omnibus significance level, but for the purposes of this video we're still going to do some post hoc tests because they are necessary to know. And in all cases, as far as did we achieve our critical difference as far as our observed differences are concerned? In all cases, that is false. And in the more focused post-hoc test, they're also false as well. It looks like we haven't really been too close in all cases to achieving the critical differences. It looks like in our high, medium, and medium none comparison, we're marginally close, and again, high, medium, and a little bit more focused of our approach. And if we look at the John here results, it looks like we do not have a significant trend in our data. Okay, thanks.